And that's why I want to come back to fractals, because they give us a very, very, very different picture on this problem. Now, we need to think pretty big here, and your initial reaction might be to say this is a bit ridiculous, but I'm going to say, suppose the whole universe is a deterministic dynamical system evolving on some, now not weather or pendulum or something like that, but some humongously big state space. Trouser space on steroids, if you like. It's every particle in the universe, is contributing to this state space. But nevertheless, suppose there is some kind of fractal attractor. Now, one important point is that it's kind of a consequence of the Gödel-Turing stuff, is that there is no formula. There is no simple thing I can code up on a computer that will tell me, for example, where exactly this fractal is in the state space. I know it exists, but I can't do a calculation which will tell me categorically that a particular point lies on the attractor or doesn't lie on the attractor. But before I get to that, let's stop for a second. And you might say, well, look, pendulums, okay, the weather, okay, but the universe? The universe is really dominated by gravitational effects on large scales. And I haven't talked about gravity at all. So is gravity chaotic? You bet it's chaotic. In fact, the very first example of chaos was actually shown by French mathematical physicist Henri Poincaré right at the beginning of the 20th century. And here's a really beautiful illustration of what Poincaré found from a very sort of theoretical point of view. This is Simon Tardivel's animation. We're looking at 4 gravitationally bound bodies. I'm going to show you an animation any second now. And, let's watch them. Yep, there they go. So they're orbiting around each other in 4 really nice ellipses. And it actually looks extremely predictable, doesn't it? Until, whoa. It's such a beautiful result. I'm going to show it again, because I just think it's so... I've looked at this, and this is... By the way, before I start the animation, this is another beautiful illustration of this feature of chaos, that the instabilities in chaos can be very localized in state space, and their manifestation can be very intermittent. This is why, there is some plausible belief that some of our financial crashes and maybe conflicts and things like that are when our social systems approach some of these very intermittent instabilities and blow apart. But we're seeing exactly that process here. We've got 5 periods of oscillation where these bodies seem to almost describe perfect ellipses, and then on the 6th one or something, they just zip off to infinity. Let's look at it again, because it's so nice. So there they go, and you imagine trying to do a prediction. You might say, they just carry on like that forever. Why not? They've done it in the last 5 episodes. Bong. Okay, so that's that. So chaos. So absolutely, chaos occurs in gravitationally bound systems. So I hope this idea that the universe could be indeed a chaotic system evolving on a fractal attractor is not completely bonkers. So with that in mind, let's go back to our Bell experiment. So what I've drawn here are 4 points corresponding to states of the universe on Monday, Tuesday, Wednesday, Thursday, where Alice and Bob do their 4, if you like, sub-experiments. They compute the 4 different correlation functions that eventually go into the Bell equation, the Bell inequality. Now, by construction, by my hypothesis that the universe is a deterministic system evolving on a cosmological fractal attractor, these 4 points must lie on the fractal attractor. So I've drawn them, I've drawn the points, lying on one of those trajectories. So that makes it all nice and consistent. But now what I'm going to do is draw the counterfactual worlds where we hypothetically, because this didn't happen, but we hypothesize that we are taking Monday's particles and measuring them with Tuesday, Wednesday, and Thursday's polarizer settings. So I have to take Tuesday and somehow perturb the true state of the universe a little bit to reflect the fact that I'm no longer dealing with Tuesday's particles, but Monday's particles. And similarly, for Wednesday and Thursday. So the white dots are these hypothetical counterfactual worlds whose reality is needed if you are to prove the interpretation that Bell's inequality or the Bell experiment requires spooky action at a distance or indeterminism. Now I'm going to zoom into this because what I've done is deliberately put Wednesday's counterfactual in a fractal gap, in the sense that it now violates my assumption that any realistic states of the universe have to lie on the fractal attractor. So what it means is that Wednesday's counterfactual, according to this illustration, is not a plausible realistic state. In other words, it's inconsistent with this notion that the universe is a dynamical system, a deterministic dynamical system evolving on a fractal attractor. Okay, well, look, I've just drawn it there, but it turns out, I have papers written with colleagues, some by myself, some with colleagues, which show that this is actually can be made into quite a rigorous idea, and that at least one of these three counterfactual worlds must lie in a fractal gap, and hence it's not physically real. And that's enough to explain Bell's experiment without invoking non-locality or indeterminism. Okay. That may seem a slightly sort of technical thing. What is this saying in a more big picture way? So what I want to move into the next slide is what this is really saying about physics in the big picture. What is the real message behind the Bell experiment, if this interpretation is correct? I think it signals the end of a kind of principle that has served us extremely well in the past in science, but may be running its course. And that's a kind of reductionism. Now, I'm not claiming every type of reductionism is wrong, but a particular reductionism which says the smaller we look at things, the more fundamentally we're probing the structure of nature. And it's worked, of course, extremely well in terms of our discovery of atoms, and of course, understanding atoms and the electrons that go around the nuclei has been critical for understanding chemistry, the chemistry of life, chemistry, inorganic chemistry, everything. And to understand atoms, we have built accelerators which smash atoms apart, they smash nuclei apart, and we can understand that really what goes on in a nucleus of an atom are collections of protons and neutrons, and we can smash those, and we see there are quarks underpinning all the protons and neutrons. So that's all good. But we haven't, as I say, we haven't yet managed to succeed in combining these ideas with gravity. Now, the conventional thinking behind that is that we need to get to even smaller distances before we can really understand how quantum mechanics and gravity unify. There's a thing called the Planck length. There's a thing called Planck mass as well, but the Planck length, which is absolutely tiny, 10 to the minus 33 centimeters. And the thinking is we've got to get down to these even more fundamentally smaller lengths to understand that. If this picture I've told you about with fractal geometry is right, and I do think it is at least logically correct, then this paints a completely different picture on the way we should be going, particularly with this idea of unification with gravity. Because these fractal attractors are really about properties of the system as a whole. The geometry of the Lorentz attractor is not about, one of the equations. It's something which is kind of intrinsic to the three equations together. It says something about the global structure of the system. And if this interpretation of Bell's theorem is right, then it's saying that we really have to understand how the laws of physics operate on the largest possible structures of the universe, as much as on these small scales. So in other words, kind of top down as much as bottom up. Now, this to a lot of physicists will sound extremely, even cranky might be the word. But I want to finish my talk with, I've already mentioned 2 Nobel Prize winners, one in 2022, 3 Nobel Prize winners in 2022. I've mentioned Suki Manabe, 2021. I want to finish with a couple of quotes from the Nobel Prize winner of 2020, Roger Penrose, who was a great influence on me. He taught me relativity when I did doing my PhD in Oxford. So here's a couple of quotes from Roger Penrose to make the point that this idea may not be so completely bonkers after all. And this is a quote from his book he wrote in late 1980s, I think. No, sorry, 1990s. My own view is that to understand so-called quantum non-locality, we shall require a radical new theory. This theory will not just be a slight modification of quantum mechanics, but something as different from standard quantum mechanics as general relativity is from Newtonian gravity. So anyone who knows anything about general relativity knows that it's a complete rewrite of Newtonian gravity. It's basing gravity not on forces which accelerate things, but on the geometry of space-time. And Penrose here is claiming that we're going to need that sort of revolution to understand quantum non-locality, basically the Bell experiment. And from his more perhaps well-known book, The Emperor's New Mind, he says, again, something which appeals to me that it seems to me quite plausible that the correct theory of quantum gravity might be a deterministic but non-computable theory. Non-computable in this Turing-Gödel sense of the word. And again, I would just remind you that these fractal attractors are formally of this non-computable type. So that gives us a clue that this might be in the right direction. Who knows? Okay, so I think it's probably time to finish. I've taken a couple of things from this book. I believe there might be 1 or 2 copies outside if people are interested. I certainly write in a lot more detail about stuff I've talked about and also a lot of stuff I haven't talked about, broadly under the theme of uncertainty, not only for helping us make better decisions, but also understanding how systems become uncertain actually helps us understand the systems themselves better. So I think with that point, I will stop. Thank you.